let's start out with what the heck is going on with Ed's background. So this this is the background, and this is the star of today's show, the Dirty Bubble. So I don't know if any of you are familiar with. I'm sure a lot of you are familiar with the cartoon show SpongeBob SquarePants. But in SpongeBob, he has some heroes, and one of the supervillains that his heroes fight against is the Dirty Bubble. And the Dirty Bubble is a very good analogy to what we're trying to do with geographic coverage when we're doing gas detection. And basically, the Dirty Bubble, the evil villain, this is our hazardous gas cloud. This is the cloud of toxic gas, or the cloud of flammable gas, which is capable of causing harm. And what our objective is in a geographic study or a grid-based study is to make sure that the Dirty Bubble cannot hide in the process plant anywhere without being detected. So in our geographic coverage software, what we're doing is we're kind of moving the Dirty Bubble around the map and making sure that at all points in time that at least one of the detectors is going to be able to detect the Dirty Bubble. So the big question, though, that kind of goes into this is, well, how big is the Dirty Bubble that we're worried about? What is the size of the Dirty Bubble that is going to cause us to be concerned and cause us to want to detect said Dirty Bubble? And a lot of people are going to use a 5-meter radius. A lot of other people are going to use a 5-meter diameter. But where did that number come from? So it's very common in the process industries to lay your detectors out on a 5-meter grid. But why would you do such a thing? Well, let's get into that. And I'm going to be jumping around. I have like a whole bunch of presentation slides, and I've got a whole bunch of web pages that I'm looking at. So let me begin with a great source of information in general, which is the Conexus website. And we do a lot of posts that basically talk about technical topics. And one of the ones that I wrote many moons ago, I'm trying to figure out if there's a date on this somewhere, but at least 10 years ago, is the origin of the 5-meter grid. And what you're going to realize is that a lot of the work was done by the UK Health and Safety Executive. Well, technically, they outsourced it to Lloyd's of London, which I believe now has been spun off, and it's a company called Visus. But they did a little bit of the research to determine why a 5-meter grid makes sense. But then also I will explain why it doesn't make sense in a lot of cases. There are a lot of assumptions built into what you're doing that might make that 5-meter criteria inappropriate for what you're doing. So you can take a look at this, and I'm going to highly recommend everybody research this report, and I'm going to show you the report. It's right here, and I'm going to show you different pieces. I'm going to spend a lot of time in the report to explain where things come from, but let me back up even a little bit further from there. So for those of you that are familiar, what you're looking at here is the good old Texas City gas plant that we at Conexus use for our training and our demos. And I'm showing you a representation of geographic coverage for a series of detectors, a series of gas detectors. So when I kind of scroll in, you can see the location of each of the detectors. So there's a detector here, detector here, detector here. These are point source detectors. And the point source detectors are what the 5-meter grid is really based on. there's kind of the assumption that we're going to put in a point gas detector on a 5-meter grid. And also in effigy, you have the ability to use open path detectors. So if you look here, I've got an open path detector. Now, around all these detectors, you're going to see these yellow bubbles. So the yellow bubble is the 3D representation of the covered area, or the covered volume, if you want to think about it in 3 dimensions, for a gas detector. So the theory is that if the center of a gas cloud, well, actually, let me back up. Right out of the gate, this is very misleading to say, and basically what you're saying, well, is if there's a gas cloud inside this yellow bubble, inside this yellow circle, it's going to be detected. And that's absolutely false. Gas detectors don't have a range where if there's a gas inside that range, they're going to be able to detect it. There's approximation stacked upon assumption, stacked upon approximation to kind of come up with this thesis. And that's kind of what I'm going to unpack today, is what all those assumptions are and what the thesis is. But in reality, what we're saying with this type of figure is that if there is a spherical gas cloud, kind of like our good friend the dirty bubble. So if there is a spherical gas cloud that is inside, whose center is inside this yellow sphere, then that gas cloud will overlap with the detectable, or overlap with the detector at a concentration where the detector will sense the presence of the gas cloud. So the coverage, if you will, of this detector being that sphere assumes that all of your gas clouds are spheres, and that the edge of the sphere is going to be at a concentration that matches with the set point of the detector. Now, in reality, the only way in the real world for you to get a spherical gas cloud is to put it inside a bubble or put it inside a balloon. In the real world, gas detectors are not spheres. So that's the first thing that kind of throws some kinks in the works and makes the makes you kind of understand that this whole grid spacing and geographic coverage is really oversimplified to try to create an easy solution to a difficult problem. And now granted, it's a great starting point. 20, 30 years ago, it was the highest tech. Right now, I'm definitely going to push you to go to geographic coverage as being a lot more realistic, but that's kind of where it all started from. Okay, so what we're saying is if the dirty bubble if the center of the dirty bubble is inside this yellow circle, then it will be detected by a given detector. And therefore, if I go ahead and I say, okay, well, let me look at this elevation where I expect the detectors to be located, and then I'm going to show the geographic coverage for gas detection. Now, when I look at it at this 2D view, and actually let me just drop out to a plot view instead of a 3D view. Basically, if you look at that one slice of the 3D model, then what you're saying is that anything that is, if the center of the dirty bubble is on this side, the dirty bubble will be detected because it's going to intersect with gas detector 7. But if the center of the dirty bubble is over here in the red, that gas cloud will not be detected because it kind of slips through the cracks. It doesn't fit into, there's no location where that dirty bubble is going to intersect with the gas detector. So that's how the geographic mapping, whether you're looking at it in a volumetric basis or looking at it in a slice of the three-dimensional model, That's how the calculations get performed. So if you look here for this entire zone, 16% of the zone, if it's green, that means that the dirty bubble is going to intersect with 2 detectors. If it's yellow, only 1 detector. If it's red, no detectors. Okay, so that's kind of how geographic coverage works, what we're doing in geographic coverage. But one of the key things that we did, sorry about that, let me pan. So if I go here to gas detector number 5, why is the size of this covered zone the size that it is? And basically, we're not actually looking at, well, how big of a gas cloud do we actually think we're going to get? What we're saying is, what is the smallest gas cloud that's capable of causing harm? So that's another simplification of geographic coverage versus scenario coverage, is that geographic coverage doesn't care what a gas cloud is actually going to look like. It doesn't care how big it's actually going to be. It's basically saying, what size of gas cloud am I worried about? And for most of you, that's going to come from your corporate standards, or if you're an EPC or an equipment vendor company, you're going to look to your client's corporate standards for telling you how big of a gas cloud I need to detect. And in some cases, that'll be a 5-meter diameter, maybe a 5-meter radius, maybe it's a 7-meter diameter, maybe it's a 10-meter diameter. Well, how do we make that decision? Well, once you made the decision, in effigy here, you simply click on a gas detector and say, okay, for this detector, I'm trying to detect a gas cloud with a critical diameter of 32.8 feet. And for those, everyone here is an engineer, so you're very adept at unit conversions. That's going to be 10 meters. So in this case, we set this up to look for a 10-meter cloud, 10-meter diameter cloud. And kind of going back here, basically a simplified version of the software, and that's not how our software works. All you would do is find the location of that detector and draw a sphere with a 10-meter diameter around it. And if you're inside the sphere, you're detected. If you're outside the sphere, you're not detected. Okay, so that's kind of a lot of background on what we're trying to do, how we're trying to do it. But where did the number come from? Why is 10 meters okay? Why is that the number that I'm concerned about? And it all has to do with what is the gas cloud that can cause harm. That's what I'm really interested in. That's what I'm really worried about. And in order to kind of flesh this out a little more, bear with me for a second. So let me come back here now, and I'm going to show a little bit out of a more advanced Connexus training class, theory and methods for fire and gas, where we talk about gas detector coverage assessment, and we talk about the different philosophies for gas detection. So fire and gas mapping, placement of fire and gas detectors is a little bit of philosophy, it's a little bit of art, and it's a lot of science. And the first thing that you need to determine when you're trying to lay out your gas detectors is, well, what am I really worried about? Am I worried about a release source? So is there something that's releasing gas, and I'm worried about making sure that I can detect a release from that piece of equipment? Maybe you're not worried about releases, maybe you're more worried about accumulation. You have areas in your plant where things become stagnant and gas can accumulate. And then you might also, the third philosophy would be to look at migration. So you're not so much worried about a gas plant existing in your facility, but if it's going to wander off of your plot plan into a neighborhood that's next door to your plant, then at that point in time, you're worried about detection. So there are different philosophies for gas detection. Different methods have different strengths when you're looking at things. So when you're looking at this geographic method, the key item in the geographic method is to determine what your critical cloud size is. And I already showed you in effigy where you would enter in the critical cloud size when you're doing a combustible gas detection. So what we're trying to do is we're not determining what is a gas cloud actually going to look like. So if you're looking at geographic coverage, what actually happens? The actual gas cloud you get is completely irrelevant. We don't know what it is. We don't care what it is. So we're not doing any kind of dispersion modeling. We're simply trying to say, well, if there's an accumulation of a gas to a certain size, how big does that accumulation need to get before I am worried about it? So what is the smallest gas cloud that is going to cause a significant amount of harm to where I will want to detect a gas cloud once it gets to that size? And what we're going to see when we get into that HSE report, that the determination of how big that gas cloud is that I'm worried about is going to be all about how fast does my flame front move once the ignition of the gas cloud occurs. Because the speed of the flame is going to determine the amount of overpressure. So what is overpressure? Overpressure is the difference between atmospheric pressure and the pressure at the peak of the shell of compressed gas that's created by the explosion. And that overpressure determines the amount of damage that that shock wave is going to do to structures, equipment, and people. So something as small as a half PSI or 1 PSI of overpressure is going to be enough to shatter glass. A 3 PSI overpressure is going to be sufficient to knock over, to damage, to collapse cinder block construction buildings. And as something like 5 to 10 PSI overpressure, any kind of normal construction is going to get leveled by that degree of overpressure. So we want to know, if I ignite the flame, how fast is the flame going to go? Because until the flame gets supersonic, the compressed gas shell is going to have a very minimal overpressure. Now, what you're going to see when we get into the report is that a 5 meter or smaller diameter cloud does not have enough fuel to cause a strong blast. Technically, yes, insufficient fuel, but in reality, what we're going to see is that there's not enough distance for the flame to travel to cause the flame to go supersonic and to cause that compressed gas shell with the shock wave. So there's a point in time where you're going to be able to develop a flame front that's sufficient to cause massive amounts of damage. But if the distance that the flame travels is less than 5 meters, and that's where the 5 meter grid came from, then you're going to get a flash fire. You're not going to get a vapor cloud explosion. Again, all of this is completely divorced from what will actually happen when you release gas from your process. It's more of a theoretical, when I release material, how much do I have to release? How big does that gas cloud need to be before it's actually going to cause damage? So this is kind of where that 5 meter grid came from. And in reality, if you look at the 5 meter grid, so if I lay out items on a 5 meter grid, so every one of these distances is 5 meters. In reality, you can have a gas cloud that's bigger than 5 meters inside a 5 meter grid. So if I could draw the dirty bubble, in here. So there's the dirty bubble. He can act if he's sitting in between all the detectors. His radius can actually be bigger than 5 meters. Well, what's the actual limitation? What's the actual longest pathway that a flame can travel in a 5-meter grid? Well, we will talk to our good friend Pythagoras, because we have a right triangle here. So what we're going to notice is that actually the maximum flame length is going to be approximately 7 meters in a 5-meter grid, because that's going to be the hypotenuse, and that's going to be the longest distance that you're going to have in between any detectors. And 7 meters is actually more accurate for what we're doing. Now, all of this discussion of this 5-meter distance came from this OTO 93002, which I'm going to get into in just a second, that defines what we're looking for in terms of gas clouds. So here's kind of a table out of our guidelines for kind of what you should be looking at. And you'll notice that our guidance is if you're in a grade C area, so you have open areas with low confinement and low congestion, you can have a bigger gas cloud. We have other guidance that says, depending on what material you're releasing, you might actually want to go smaller than 5 meters on a gas cloud. So where is all of this coming from? And the answer, I'm going to step back out of here, is here's kind of an overpressure versus distance thing that I'm going to get into. So let me jump out of the PowerPoint slide, and right now I'm going to go into kind of the key document that defined all this, which is OTO 93002. So I'm going to kind of scroll around here, and I'm going to jump in and talk about some of the testing, some of the analysis that was done. So I will give all credit where credit is due. This was done by HSE. I am a big fan of HSE. They do yeoman's work in analyzing risk situations quantitatively, effectively, to provide really, really good guidance. Now, this is done a while ago. So this report, OTO 93002, we're looking at gas detector sighting criteria for detector spacing. So here we're talking about the time frame way before we're doing 3D modeling to place gas detectors. This is before the time frame of fire and gas mapping, we really didn't have the computer technology available. And as I mentioned, a lot of the work was done by Lloyd's. And shout out to any Visis people who are in the crowd right now. Lloyd's of London kind of spun out their consultancy, and it is Visis now, if you're interested in talking to those folks. Let me come back in, and I'm scrolling through here, and I'm going to give some of the key criteria. So in terms of key criteria, so sorry about that. I thought I selected there we go. A possible strategy for 1 second, here we go. A possible strategy for sighting flammable gas detectors on offshore oil and gas installations rests on the hypothesis that if a flammable gas cloud up to 6 meters in length is ignited, it will not produce flame speeds greater than 100 meters per second. And a flame speed of 100 meters per second is not expected in producing overpressures in excess of 150 millibar. So you'll have to do your own unit conversion to convert millibar into PSI, but that is not a significant overpressure. So right out of the gate in the executive summary, they say if we have a 6-meter length cloud and we ignite it, we're just going to get a flash fire. We're not going to get an explosion. And we don't want a flash fire, but we can live with a flash fire. So we're not going to try to detect anything smaller than that. But if the gas cloud is bigger than that, then your flame speed is going to be able to exceed 100 meters per second, which is going to cause you to exceed 150 millibar. And now that shock wave is going to be able to cause damage. Okay, kind of moving on a little bit, you'll see that in the study, if I've got a stoichiometric mixture, I've got a 6-meter long methane cloud or propane cloud. All right, so right out of the gate here, let me switch to red and start kind of noting some things. Right out of the gate, we are making some assumptions. When we say a 5-meter gas cloud, what we're actually assuming is that we have a methane gas cloud. Because when you change the material that you're burning, the flame speed is going to change. So for methane, the flame speed is 100 meters per second, but for propane in the same test, the flame speed is 125 meters per second. So the spacing, the size of the gas cloud necessarily needs to change based on the material that you're burning. Some material is more reactive than other material. So the more reactive the material, the smaller the distance that the flame has to travel before it gets into an explosive flame speed. Okay, so and we noted that in these cases the if the flame speed is less than what we mentioned above, then that overpressure, and the overpressure is the key to determining how much overpressure you get. So right out of the gate, I mean, kind of big picture, we said, well, if we place stuff on a 5-meter grid, we should be okay. But that 5-meter grid is actually based on a 6-meter traversal distance for the actual flame, as opposed to a 5-meter. So that's another thing to keep in mind as you're doing this analysis. Now, when we say this 6-meter item, you'll notice right here it says the inclusions above are expected to be valid for flammable gas species likely to be found in large quantities on offshore oil and gas production platforms. So right out of the gate, you should understand that if you're not on an offshore platform, maybe the material you're releasing, that 5-meter grid is inappropriate. And I'll give you one great example. If you're releasing ethylene oxide, it is wildly reactive. So it is going to come to an explosive flame speed at, much, much, much smaller than 6 meters. Okay, so what you're releasing, what you're trying to detect is going to have a large impact on, what size of gas cloud you should be working with. Now, what are some of the other factors that are going to impact the flame speed? So now you'll notice that there was a test without obstructions, and then there are tests with obstruction. So I'm going to show you what the test apparatus looked like in just a second. But when we're doing our assumptions, when we're doing our modeling, you're assuming a blockage ratio of 0.3 or 0.4. So a blockage ratio of 0.3 or 0.4 means 30% to 40% of the area where the flame is expanding into is blocked. So if I have kind of an open path. So this square represents my open pathway. And if I have piping that is obstructing my flame front's ability to expand, and I'll kind of cross that off here. So what we're assuming is that your blockage ratio is 30 to 40%. Now, if you release your gas into a completely wide open field, there is zero obstructions. But then again, if you're in a confined space, like maybe your gas cloud is inside a room that has a boiler in it, your obstruction ratio is effectively 100%. You're completely confined. And the degree of confinement is going to dramatically impact what flame speed you get and the amount of overpressure that you're going to get when you ignite things. So the reactivity of the species you're igniting and the degree of obstructions are all going to impact this. And even things like how energetic is the ignition source. So in our analysis, we're assuming relatively weak ignition sources. Hopefully, we've done a great job of electrical area classification and control of hot work to make sure that we don't have strong ignition sources. But if we have strong ignition sources, our flame speeds are going to be considerably higher. So all of these things, confinement, species of material released, energy of ignition sources, are actually going to change what your critical gas cloud size is. 5 meters to 10 meters assumes methane at 30 to 40% obstruction ratio with weak energy sources. So a lot of you have probably used 5-meter grids, probably used a 5-meter or 10-meter gas cloud in geographic coverage. Think back to the projects that you did. Were they for methane in a 30% obstruction ratio for weak ignition sources? If not, your answers might not be valid. All right, so let's kind of move on a little bit in this report. Going through the introduction kind of hits that, the main point of the analysis again, which is 6 meters. Gas cloud is what we're concerned about. And we're going to be able to get that with a 5-meter grid with alarm levels set at 20% and 60% of LSL. So LFL, that's the recommendation. The other thing that I'm going to get to is the fact that when a detector goes into alarm, that location technically is not flammable yet. If you set your detector at 20% of LFL, when the detector initially goes into alarm, if a source of ignition existed at that point, it would not ignite the gas cloud. So you're actually detecting a bigger gas cloud than the gas cloud that is capable of being ignited, which is actually even different from the gas cloud that will ignite once the ignition occurs, which is actually closer to half of LFL than LFL. So more of that coming up as we get into it. And so all of this stuff was done with flame acceleration testing. Here is the main reference. Another great read. If you haven't looked at this report, I would highly recommend going into the report. What you're seeing here from HSE is just a summary of this work that was done in the early 80s in Norway with a bunch of mixtures, and I'll show you the apparatus. Here's a description of the experimental rig, and basically we have a steel tube that has a 10-meter length, and we're putting annular rings in to create a blockage ratio. And we're doing this at 5 positions along the tube. And then we're basically going to fill the tube with gas, ignite it, and take measurements. So let me go ahead and show you that apparatus. Before I do that, we're going to come back to the experimental results that talk about something called terminal flame speed and peak overpressures. But let me jump kind of toward the end, if you'll bear with me, and show you what the apparatus looks like, and then I'll show you some of the key items. All right, so we're going to talk about this because it actually shows some of the results of the testing and shows how you need to modify what you're assuming in your calculations depending on what the species is and the obstruction ratio and so on. Here are some time distance plots for flame propagation, more time versus overpressure for different scenarios. But here is the one. This is the big dog. This is what I wanted to actually show you. So here is our a representation of our experimental apparatus. So let me try to draw on the screen and explain what's going on. So the first thing is you'll see that there is an expanding. So here the duct is 5 meters on this end, and you'll see that the duct is going to expand to 20 meters on the other end. And the distance of travel that we're taking measurements on is going to be 30 meters. So how are we running this experiment? Well, you're going to bring gas in to the front side of the test apparatus. So we have fans here that are going to supply our combustion air. And then we are also going to have a gas supply here. So this is our gas supply. There's going to be regulation equipment so that we know the flow rate of air. We're going to pipe in a certain flow rate of gas to get ourselves a stoichiometric mixture. And as you're going to see, there are going to be different flow rates of gas, different types of gases used. And that gas is going to come into the experimental apparatus back here on this side, and it's going to be allowed to fill the chamber. So as time progresses, we're going to fill this entire chamber with a stoichiometric mixture of a fuel and air. Once the chamber has been filled, we're going to create a source of ignition at this end, and then that's going to cause the flame to travel through to the end. Now, as the flame is traveling, there are going to be, sorry about this, the software wants to rescale and draw simultaneously. So there are going to be pressure measurements along the flame path, a lot more than this, that are going to allow us to measure that shock wave as it's traveling through the apparatus. Okay, furthermore, you see these obstructions. So I'm going to kind of draw a red line through an obstruction. So there's an obstruction that's creating that obstruction ratio. So what happens, what you'll see, and let me give myself some space to draw what's actually going to happen. I'm going to draw two figures. So this is x. X is going to be the distance from start. So up here where you put in your source ignition, this is going to be 0, and we're going to take measurements all the way to the end, which we said was 30 meters. So from 0 meters to 30 meters, we're going to take measurements, and then we're going to do a couple graphs. So the first graph is going to be flame speed in meters per second. And the number that we're worried about is going to be about 100 meters per second. And what you'll see, and I'll try to, I have a much better graph somewhere else that I was not able to locate, but I'll try to piece through the figures in the rest of the report to try to show you something. But for just like one study, what you're going to see is that the flame speed is relatively steady, and then the flame speed will take off exponentially. So here, in this portion, I'm going to kind of draw a line at this inflection point. Here, we're going to say this is a laminar flow. So the flame front is going to move through the combustion mixture in a laminar way. And then there's going to be a trigger point where we're going to move from laminar to turbulent. And as soon as you introduce the turbulence into the flame front, then the flame speed starts to shoot up. And once it shoots up, now you're going to quickly get into what we're really worried about is there's a point where you're going supersonic. Once your flame front goes supersonic, now the flame isn't going to travel in a laminar fashion. It's going to be moving faster than the material can effectively get out of the way, if you will, and you're going to start building up a flame or a shock wave or a shell of compressed gas. So we're really worried about this point where we start to go turbulent and kind of ramp up. And I've got some numbers down here, but what you're going to see is that and let me draw the specific case, and I'm even going to change my color. So for methane at 30% blockage, this inflection point sits there, and basically you're going to see this is going to be about 6 meters. We're still laminar, and about 7 meters we're up into that inflection point where we're starting to go supersonic. So that you'll see that once you get there, that flame speed, it's laminar, and then boom, it's going to go up. And that point where it transitions into supersonic, that's what we want to avoid, because that's what's going to cause our vapor cloud explosion. And this is kind of where that conclusion came from that said, well, 6 meters is what we're worried about, so let's put our materials on a 5-meter grid and do 20%, 60%, which even gives you a little bit more cushion. Now, this is flame speed. Flame speed in and of itself does not cause overpressure. So if I take that same kind of figure and I look at distance, 0 to 30 meters, and here I'm going to say overpressure, you're going to see kind of a similar thing. Your overpressure is going to sit flat until you get to this supersonic inflection point, and then it's going to go up dramatically. It's not going to spike up like the flame speed, but it's going to go up dramatically because it really doesn't take that much overpressure to be able to cause damage. So this overpressure is a proxy for how much damage the flame front is going to cause when the explosion occurs. So this is what we want to limit. And so basically, we just ran tests. So what can you do in these tests? Well, I can put in material that is methane, or I can do this again with propane. And when we did it with propane, you saw that at 6 meters, instead of, and let me use a different color to represent this, we'll go with purple. For propane, instead of, this is higher at 125 meters per second, whereas the methane was 100 meters per second. So you can change the material that you put into the test apparatus, and then also we can change the obstruction ratio by adding or removing these obstructions to see how things work out. Okay, so that's the test apparatus. Now let's look at the actual test results. And I'm going to start by looking not at the graphs, but I'm going to look at the table. So here, if you do nothing else with this information, let me rotate it. This table highlights for you how changing the different parameters is going to change the end results. So let me start out with test number 1 that is closest to what we did. Now, what I showed you on that previous slide was the wedge model. So the wedge model, you saw that it was a duct. It was kind of a squarish duct that started narrow and went wide. So there are different apparati, where they run tests in a pure rectangular duct. They ran things in the wedge. The first thing that they did was run things in a tube. So instead of a wedge, you simply just take a piece of pipe and then put your gas mixture in this end, and again you're doing all of your pressure measurements along the tube. So there are different apparatuses that were used in the testing, and even with propane and methane, there was a scale model of a plant that was used. So this study was, it was really comprehensive. What else got manipulated during this testing? So sometimes there was confinement, sometimes there was not confinement. So yes and no. So species of material, type of testing rig, and whether the material was confined or not. So if the material is not confined, you're much less likely to generate an explosion. And then if you are confined, what type of confinement? So there were concentric rings, so if you look at the tube, you can put an annulus in the tube, kind of like an orifice plate, if you will, to be used as the obstructions. A tube array is what I showed you in that previous picture, just kind of putting a whole bunch of piping tubes in. And then even, we have a plant. Next thing, in order to get a comprehensive assessment, we looked at, what is the spacing of the obstacles? Is the spacing random? Is the spacing consistent? How many obstacles? 1, 2, 3, 4. How much were they spaced out? And then ultimately, what is that blockage ratio? So 30% blockage ratio, 40% blockage ratio. And then even furthermore, we looked at different concentrations. So I alluded to the fact that tests were done stoichiometrically. Stoichiometrically meaning the number of moles of fuel and the moles of oxygen match exactly, so you get as complete of a combustion reaction as is possible, within the margin of measurement error. But they also did lower concentration, so closer to the lower flammability limit, to determine what flame speeds they will get to. Okay, so all of this kind of on this side is going to be input data. So it's kind of the settings for the result. On this side, these are the actual results of the testing. So in terms of the results of the testing, let's go through a few things. So I want to look at methane. So methane, again, it's key, especially in oil and gas production. And you have to remember that all of this testing was done with the industry of offshore oil and gas and production in mind, and their primary flammable of concern is methane. That's why there was a lot of focus on methane. And that's another reason why, if you're not using methane, 5-meter grid, 5-meter critical cloud size for a gas might not make sense for you. Okay, so what we noticed is if we have a 30% blockage ratio for a 9.5, so it's definitely in above the lower flammability limit, but it's not anywhere near stoichiometric. We're getting a flame speed at 6 meters of 100 meters per second. That's that critical point where if we're faster than 100 meters per second, I want to be able to detect that gas cloud. If we're less than 100 meters per second, I don't care. It's just going to be a flash fire. And also in the apparatus, they calculated the peak flame speed. So you were able to get up to 200 meters per second in the first apparatus. Now, the same exact test using propane, but at a lower volumetric ratio. And remember, propane has a lot more mass per molecule than methane. So you're probably getting the same amount, or you're getting a similar amount of reaction, even though the volume over volume is different. In this case, we went to a flame speed of 125, still maxed out at 200. So right out of the gate, propane, by that measure, propane is more reactive than methane. Once the reaction starts, it's going to generate more energy. The reaction is going to go quicker than with methane. Now over here is the item we're really worried about, and that's the overpressure. The first two tests didn't measure the overpressure at 6 meters. So let's say that this pressure detector is at 6 meters. This one is at 30 meters, which is kind of the end of run. So they didn't measure the overpressure at 6 meters, but they were able to detect that they went up to all the way up over 2,500 for methane and 4,000 for propane. So again, propane, more reactive, more combustion energy released per mole of reactant, and the explosive overpressure is almost double what the methane explosion was, with a lower volume to volume ratio. So methane. So basically, what you're seeing here is that propane is actually significantly more dangerous if it's ignited than methane is. Key, critical point, you need to be concerned about what you're actually releasing, because that completely changes the parameters. Now, all of this was done at a 30% obstruction ratio, but when you look at unobstructed releases or lower obstruction ratios, so look at all these methane releases, and this is in the wedge, but if there is no obstructions, the flame speed never gets very high at, never gets high in the unobstructed. I'm sorry, wait, that is, it's basically, it's in an unconfined. So confinement is, let me explain now a little bit about why confinement and is going to increase the flame speed. So basically, look at this chart, and I highly recommend you download this to look at the different obstruction ratios, the different items like cyclohexane, natural gas, and what overpressures you're able to achieve at different degrees of confinement, different obstruction ratios, different mixture concentrations. Okay, now if I have a flammable gas cloud, so actually let me draw it like a gas cloud. Let me do this. All right, so if I have a flammable gas cloud here, and I create a spark in that gas cloud, I am going to get a flame front that is going to travel, and that flame front is going to travel at the, ready for this, laminar burning velocity. This is if it's not highly reactive. So things kind of are going to, that flame speed is going to be relatively constant through. So if you were to instead kind of release this in a pipe, so let me redraw this a little bit. So now I'm going to draw a pipe. Your flame front, kind of laminarly, would you're going to get a little bit of surface friction with the wall, but your flame front is going to kind of look like this. Man, my drawing skills are not good. Now, what happens when you have obstructions? So if I have an obstruction, let me draw this, and I'm going to draw an obstruction. Actually, let me draw the obstruction a lot bigger. When I do this, you'll see my flame front is kind of traveling as a plug in a laminar manner, but things change when I hit the obstruction. When I hit the obstruction, some of the flame can continue in the laminar fashion because it's unobstructed. But the gas that's here has to speed up to go around the obstruction. So we're getting kind of that Bernoulli effect, the same Bernoulli effect that allows a plane to fly, because the material has to go faster over the top of the wing than the bottom wing, which is going to create a lower pressure. Or did I switch that up? Doesn't matter. You're creating a pressure differential because some of the material needs to travel faster than the rest of the material for the overall flame front to continue going at the same speed. So this introduces material that's going faster, and when that material that's going faster gets back to unobstructed, it doesn't really slow down, it just kind of changes direction. So we're going to get all this mixing, and that's where the turbulence comes from. And as you get more turbulence, the flame is going to go faster. So that's the reason it might be kind of counterintuitive that putting something in the path of the flame front is going to make the flame go faster. But hey, at the same time, if you look at a golf ball, why do golf balls have divots? The divots are there to create turbulence, which actually reduces the amount of drag and allows the golf ball to go further. So that's why the degree of confinement is going to be important. So let me go ahead and really quick, that's kind of the big message of what's going on here. Let me kind of scroll through the rest.
Hold on, Ed. We got a question out there.
Yeah.
It says for these bubbles 5 or 6 meters, is wind speed considered in the study? Isn't that important?
Wind speed, wind direction is very important, but geographic coverage does not consider it at all. The size of a gas cloud that can cause harm is completely 100% detached from the actual release scenario. We're only looking at a stagnant stoichiometric cloud and how fast can a flame travel through that stagnant stoichiometric cloud. weather conditions have no impact. So when you're doing geographic coverage, it's easy, it's simple, you can do it fast because you're ignoring everything about wind speed, wind direction, locations of obstructions. All that is completely ignored when you're determining a critical gas cloud size. In a critical gas cloud size, you're assuming that you have a stagnant spherical gas cloud. And how big does that stagnant spherical gas cloud need to be to generate a certain flame speed, which is going to generate a certain overpressure? I mean, really, I think part of what I'm doing here is I'm explaining where these numbers came from, but I'm also highlighting that the science behind them was state of the art 30 years ago, 40 years ago, but we have much better modeling technology right now. And using scenario coverage with dispersion models is going to give you a much more accurate assessment. But no, the critical gas cloud size has absolutely nothing to do with dispersion modeling, weather conditions, wind speeds. None of that. None of that is factored when you're doing geographic coverage. Okay, so here's some time of arrival, so kind of a distance from the point of ignition versus the time where the flame front arrived. Actually, let me go ahead and spin this a little bit. Bear with me. So yeah, here's some overpressure versus time. So what is the peak overpressure? How long did it take to get to that overpressure for some different scenarios? Time, distance, that's kind of one of those funky meta units. There's the test apparatus. This was the wedge apparatus. And again, they did testing in rectangular ducts and also spherical piping. This is just the wedge apparatus, which is the most complicated. Distance from ignition point versus time. So that's time of travel of the item. Distance, peak overpressure versus time. Yeah, the information here is a little bit dense. You're probably not going to be able to make a lot of, oh, this is the one I'm looking for. So this is a good one. Let me rotate this one more time. So this is, I kind of showed you my hand drawing of flame speed versus distance, but this drawing really hits home. So you see that we're worried, kind of in our conclusions, we said, as long as our flame speed is below 100 meters per second, we're not going to generate significant overpressure. And here is just one test where we're measuring the flame speed versus the distance. And you notice from 1, 2, 3, 4, 5, 6 meters, 7 meters, the flame speed is relatively small. It's below 200 meters per second for sure. But there's a point in time here at that 7-meter trigger where you just shoot. You just shoot up. This is what we're worried about. Once we get to that point, now our gas cloud is big enough to where we've put ourselves in a world of hurt, if you will. You're going to get shock waves that can cause massive damage to big pieces of equipment. So that, you'll see kind of 7 meters is where it took off. 6 meters, we kind of spiked over 100 meters per second. Not the end of the world, but right out here, this is where things really took off. So that's kind of where we're going. And 7 meters, if you remember, if I have my 5-meter grid, my hypotenuse is about 7 meters. So basically what you're saying is if the dirty bubble is 7 meters in diameter, then he's not going to be able to hide in this grid anywhere. Assuming the center line of the gas cloud is the same elevation where the detectors are located. If the gas cloud is above or below, all bets are off. Okay, and here, there we go, is that the flame speed versus overpressure. So you see an exponential. It's not a linear rise in overpressure versus flame speed, but if as you're getting up to 100, and here the units are going to be in bars. So for those of you that are a little bit metric deficient, 1 bar is about 1 atmosphere. So this is going to be about 15 psi overpressure. 15 psi overpressure will be able to destroy most blast-proof buildings. So that's that's real bad. So yeah, we definitely don't want to be there. Even if this is 7.5 psi, an explosion-proof building will be able to contain that. So that's around 200 meters per second. So yeah, once you get down here, now we're looking at kind of the 0.1 range, which 1.5, maybe we could shatter glass, but it's not going to be able to knock equipment over or collapse buildings. So yeah, you see there's a relationship here between flame speed and overpressure, and as long as our flame speed is below 100 meters per second, we're probably going to be okay. So our goal when we're setting the critical gas cloud is, what is the degree of overpressure that we're worried about? Let's say, it's 0.1. What is the flame speed that can cause that overpressure? What is the distance that the flame has to travel in order to get to that flame speed? And that's my critical gas cloud size. And as we saw, and I'll come back to that in just a second. Let me scroll myself back up to those tables that we were looking at. That distance is going to change depending on what species we're concerned about, what degree of confinement we have, what blockage ratio we have, and it's going to depend a little bit on volume to volume ratio. So this is a table, flame speeds. Now, if you go out in industry, you're going to be able to find a lot more sources of information. So that's a very long explanation of where the numbers came from, but ultimately what we're trying to do, if I could back us up, if I could back us up to what we're trying to accomplish, we're trying to say, well, I don't want our good friend, the dirty bubble, to be able to hide in my plant. So I know that if the center of the dirty bubble is inside this yellow sphere, that I will be safe, or I will be able to detect it. So how big does the dirty bubble need to be? How big of a dirty bubble do I need to be afraid of? And that number is going to be, how do you like that? The number that I'm not even gonna do there. Go there. Let me go. I'm going to go ahead actually and now jump out into my last bit of presentation to kind of summarize things. So this, what we're going into, this is the ISA EC 56 training class on fire and gas mapping, which I highly recommend. ISA has a certification for fire and gas mapping that you can achieve as part of this training class, and I'm not going to belabor that anymore. So what you're doing is you're setting the size of this cloud. That's telling you what your coverage is, and then you need to continue to lay out enough detectors until you've achieved your coverage target. So in this case, if our target was 80%, well, only 17% of the area is not covered. 67% is detected by one detector, and 17% is detected by two or more detectors. And the key parameter that went into this decision-making process is what is the diameter of that sphere. All right, so that was kind of a little bit of a scattershot presentation. Not reading off of slides. Instead, I kind of went back to the key source material and demonstrated kind of some of the key parameters for the source material, the key testing that was done to make determinations, and then also a really, I think, important understanding of what tests did we do to verify what we're doing. And now you know, kind of, if I could have one big message to sum things up. When you're doing geographic coverage, and we at Conexus don't recommend geographic coverage most of the time unless you're worried about accumulations. If you're worried about detecting releases, you should really be using scenario coverage. But if you're going to use geographic coverage, the key parameter when you're doing your risk analysis is what is the critical gas cloud size. The critical gas cloud size is what is the longest distance that a flame can travel without going supersonic and causing an overpressure that we would call an explosion. So if the distance is less, you're going to get a laminar flash fire. If the distance is more, you're going to get an explosion that will cause a shock wave. So that distance is 6 or 7 meters, typically, for a methane release on an offshore oil platform, which is about a 30 to 40% obstruction ratio. But if you're releasing something other than methane, you might need to rescale based on the reactivity. If your obstruction ratio is not 30 to 40%, if it's a lot less than 30, 40%, you could probably use a much bigger gas cloud. And if it's higher than 30, 40%, you're probably going to need to use a smaller gas cloud. And if you're completely confined indoors, well, a lot of this stuff goes out the window anyway. You should be using computational fluid dynamics and toss all this other stuff out the window. So the size of the critical gas cloud is a function of what material did you release, what is the degree of confinement of that material, and we're going to still assume you're going to get a relatively weak source of ignition as opposed to a very strong source of ignition when you're making that decision. So based on that, that kind of gives you a background into the 5-meter grid. That gives you a background into what size of gas cloud should I be picking for my critical gas cloud in a geographic risk study. Gives you some information on where you might want to use different numbers and some resources to match what you're doing versus what some of the tests have been done in industry. So with that, let me go ahead and turn over the presentation to some questions. Does anyone have any questions? Well, let me start with Chris. Are there any questions in the chat about what we've said, what I've just done?
Yeah, I see one out there. It says, in the experiment, the ignition point is close to the release point. What happens when the ignition point is on the edge of 5 or 6 meters from the release point?
Okay, very interesting question. Now, the release point itself doesn't matter. So let me explain. So if I have a piece of equipment that's releasing material and I'm going to get a gas cloud. So this is actually what your gas cloud's going to look like as opposed to spherical. It's going to be more kind of cigar shaped. It doesn't matter whether, change colors, whether my source of ignition is this way and my flame front travels like this, or if my source of ignition is over here and my flame front travels this way. You're going to get the same intensity of flame front. You're going to get the same degree of overpressure because it's a matter of distance. Now, what gums up the works? So what's going to gum up the work? The worst case scenario is igniting on the edge. And when we're doing our analysis, that's what we assume, the worst case scenario where you ignite it on the edge. But what happens when you ignite in the middle? So if I ignite in the middle, oversimplifying, I'm going to get a flame front going this way, and I'm going to get a flame front going this way. So my flame speed is going to kind of look like, instead of going like this, it's going to look like this. So this would be my ignition point. I'm going to get a flame accelerating that way. I'm going to get a flame accelerating that way. So if you ignite a gas cloud in the middle, the flame speed is going to get cut, and the amount of overpressure is going to get cut. So, I mean, it's as if you would kind of, just ignore half of the gas cloud, and you're only getting your explosive overpressure from that side, or you're just getting it from this side. So it's definitely a lower consequence scenario. The biggest consequence you're going to get is when you ignite at the edge, because when you ignite at the edge, you maximize the distance of flame travel. When you maximize the distance of flame travel, you maximize the degree of overpressure, which maximizes the amount of damage that occurs. All right, what else we got?
I don't see anything else in the chat. Does anybody have anything else?
What about toxic gas?
What about toxic gas? That's an excellent question. With toxic gas, okay, so for everything that we did here, we said, what is the size of gas cloud that's capable of causing harm? And we want to make sure in our geographic coverage, we want to make sure that if you exceed the size of a gas cloud that can cause harm, we want to be able to detect it. So if you wanted to do an analogy to toxic gas, you would say, well, what size of toxic gas cloud is capable of causing harm? And the unsatisfying answer is any gas cloud can cause harm. So any gas cloud that is above the probit value for fatality, or the probit value for serious injury, that can cause harm. Now, if you go with a philosophy of, I want to detect every gas cloud that can cause harm, you will not be able to walk through your plant, because you'll be putting gas detectors every 10 centimeters, which is not realistic. So scenario coverage geographic coverage for toxic gas clouds, it's very hard to get a rational basis to justify how big of a gas cloud I'm concerned about, because extremely small gas clouds are capable of causing harm. So let me go in, I'm going to go back into some of the criteria that we have. And again, this is kind of hard for me because, we at Conexus, for toxic gases, there's almost no reason we would ever do geographic coverage. We would always do scenario coverage, run dispersion models to see what the gas clouds actually look like. But if I could go into our criteria, there's still enough people who do it. Let me see if I can find. That's not what I was looking for. So this is for flammable gas clouds. Bear with me for a second. Let me see if... See, now I'm going completely off the cuff. Trying to figure out a design basis gas cloud for toxics. Hold tight. There's fires. Here is combustible gases. Toxic gases. Okay, so what our recommendation is, and this again is going to be in that ISA EC 56 course, which is coming up in about 3 weeks, I think, our next installment of that. You can use the critical gas cloud for scenario coverage that is basically, let me make this a little bit bigger. So what is the extent of a gas cloud that will potentially cause an injury? So how do we make that determination of what the gas cloud size is? Well, some companies will just have a number. They'll say 8 meters or 10 meters. And, you know, hey, that's better than nothing. But if you need to justify what your work is, you're going to need to do a little bit of dispersion modeling. Okay, so what we do is we figure out a critical gas cloud size based on dispersion modeling, and then we will create a detectable gas cloud that is different. So if you look at these two models, so we ran some toxic gas releases. So I've got a 5 millimeter release of sour crude oil. That's generating a pool, and that sour crude oil is releasing H2S. We used a popular dispersion modeling software to figure out what that gas cloud looks like. So if you look at the different endpoints, 700 ppm is a very small cloud, but 700 ppm is, and I'm going to have to recheck my math, but that's a 50% fatality probit. So if you expose yourself for a very short time duration to 700 ppm of H2S, 50% of the time you will be fatally injured. Which is different from 100 ppm, the yellow gas cloud, which is for immediately dangerous to life and health. 15 ppm might be the set point of the detector, and 5 ppm is the permissible exposure limit. So if you're below the permissible exposure limit, in the United States at least, that allows you to work in that environment for an 8-hour shift. So you can be exposed to up to 5 ppm of H2S for your entire 8-hour work shift. Which is why a lot of times when you're setting set points for toxic gas detectors, you're going to set it at the permissible exposure limit, because if you're above the permissible exposure limit, you need to get your employees out of there because they're not allowed to be working there for long periods of time, if nothing else. Okay, so if I set my detector, or if I'm concerned about a 700 ppm cloud, I might want to run a dispersion model to say, well, if I have a release that can generate 700 ppm of H2S, how big is the gas cloud at a detectable point? And in this case, you'll see that this gas cloud that is detectable is about 4.7 meters. So we would use that not as, or we would use that as the radius, as the diameter, not the radius. So we would want to be able to detect the gas cloud. So if I could overlay the dirty bubble over top of this, his diameter would be from 0 to 4.7 meters. And again, we did that based on dispersion modeling. And in this case, we're actually looking at what size of gas clouds do we expect to occur at your facility. Because this did, when we said, okay, the gas cloud we're worried about, or we want to detect is 4.7 meters, this was a 5 millimeter diameter release at B atmospheric stability and 1.5 meter wind speed. So all of that factored in. So unless the company you're working for just gives you a number, I would run a scenario, run a dispersion model, and figure out how big the detectable gas cloud is, and use that as the number that you would put in for your critical gas cloud size. Thanks for the question. Anyone else? All right, well, go ahead,
I was
Chris.
gonna say, I'm not seeing anything in the chat.
All right, well then I'll go ahead and wrap it up here. Thank you everyone for your time. And oh, we've got one more question. I'll go ahead and take this before we wrap up. Yes.
I have a question. Actually, I posted in the meeting chat, but I'm not sure whether, you can see it or not. Actually, I'm asking something about the so-called the location of the gas detector lah. Because actually, just to share with you lah, for most of the time when we do fire and gas mapping, we propose the location of the gas detector. Okay, then in the actual site installation, could be the location may not be exactly the same as what we propose in the fire and gas detection mapping lah. So we'd like to get advice from you, okay, whether let's say a difference of 5 meters from the proposed location, is it considered acceptable without doing any mapping? Let's say lah.
Okay, well, gas detection is a little bit more forgiving than fire detection. For fire detection, moving a fire detector 1 meter could be catastrophic, depending on where you moved it. 1 meter, you can move it in front of a piece of equipment. Gas detection is a little bit more forgiving because as the equipment moves around, any gas release is going to engulf and go around pieces of equipment. So it'll kind of disturb the profile of the gas release, but not break it entirely. At Connexus, when we issue a report, we generally give 1 meter. We basically say that our results are going to be accurate, plus or minus 1 meter, X, Y, Z, any direction. 5 meters is a lot. So, that's something that actually I might want to have some interns do a research project on to basically, move detectors 1 meter, 2 meters, 3 meters, 5 meters, and see how it changes the coverage results, both in scenario coverage and geographic coverage. But yeah, we at Connexus, we do allow some movement of the detectors without remapping. But we limit it to 1 meter. 5 meters, I have a feeling that it's not going to be that far off, but I'm a little bit nervous at 5 meters. That's nothing that I've ever allowed. It's nothing that I've ever tested to rerun something that's been moved 5 meters to see how it changes the coverage. But yeah, just gut feel without doing any calculations. I'm a little bit nervous for 5 meters. I'm very comfortable with 1 meter. So take that as it is.
Yeah. I just need to get so-called expert advice. What is the acceptable, tolerable region? Good practice is plus minus 1 meter, right? For gas detection. Even the same also for fire detection, is it?
Yeah, we allow 1 meter on fire detection. But then again, it's also something where it's kind of easy for us to look at a layout qualitatively and know that whether the movement of the detectors will actually significantly change the results. So we on paper we would put 1 meter, but we would look at the layout in comparison with the like on a plot plan in comparison with the physical pieces of equipment to see if obstructions moved in front of detectors. But yeah, we would generally allow 1 meter for both fire and gas as our good practice.
Okay, thanks a lot, Everett,
Sure,
for your
absolutely.
advice. Expert advice, thanks.
No problem. Chris, did we get another thing in the chat?
Yeah, looked like there was a delay. There's a few out there, but I see Fernando has his hand up.
Yes, Fernando.
Yes, Ed, thank you very much for this webinar. Very insightful. Is there a way to categorize the severity of overpressure levels in terms of harm? This would be for conceptual design purposes.
Yes. And what I would like to do, but I'm not going to do, is walk around the corner to our library and get a book for you.
Okay.
Instead, I will just tell you where it's at. So if you have a copy of the Center for Chemical Process Safety's guidelines for chemical process quantitative risk analysis, I know for sure that the table is in there. And actually, let me jump out of here and just do a quick internet search on table of, try this again, of overpressure versus building damage. And maybe it'll just pop up. Okay, so here's kind of an example. I don't know where this came from, but in the chemical process safety books, you will see things. So there will be there'll be tables that will say, okay, what kind of damage is of concern and what overpressure can generate that. So typical glass window damage is going to occur at 1 to 1.5. I've heard numbers as low as 0.5. So minor damage to buildings at 3 to 7. This actually is not a very good table. This one, to be honest, to me seems very optimistic. Let's go look at this one. There we go. Oh, there we go. So this one is giving you completely different numbers. Which is why you're always going to want to check your sources. But yeah, minor glass damage at less than a PSI, minor damage at around 1 PSI, sheet metal buildings buckling at about 1 to 2 PSI, concrete cinder block buildings collapsing at 2 to 3 PSI, wood frame buildings collapsing at 5 PSI. So you can find tables like this. As you can see, I did a quick internet search and came up with like 1,000 of them. So you're going to need to find a resource that you trust. The resource I recommend is Chemical Process Quantitative Risk Analysis from CCPS is going to have a table just like this.
Yeah, perfect. So the other question would be, if I may, what would be your recommendation in order to detect volatile vapors coming from liquid leakage, like for example gasoline? We're not talking about a massive amount of gas, as an excursion. We're talking about a vapor that is going to be accumulated, over time and creating a flammable atmosphere. So are we talking about maybe a line of sight or a combination in between line of sight and point detection?
Okay. It all depends, and again, I'm speaking in generalities here.
Yeah, general.
If you're spilling a flammable liquid above its flash point. So that might be in the process, it might be a storage area. If the temperature of the material is above its flash point, that means you're going to be generating enough vapor to sustain a fire, and you're going to be creating a potential gas cloud. If you're releasing that into if it's in storage, your best detection method, honestly, is going to be a level switch in the sump. Because all your liquid is just going to travel downhill. It's going to fill the sump. You've got a level switch telling you you've got a level where you shouldn't have a level. And that's the best way to know that you have a spill. Now, if you wanted to use gas detection, putting a gas detector open path over the bunded area is not a bad idea. It's not as fast as the level switch. But if you're accumulating in an area where, let's say, the spill doesn't run correctly down into your sump, you're going to be able to detect that. And if you're spilling into an area where you don't have a bunded area, you just have kind of grading and curbing, there is a place where gas detection makes a little bit more sense. Yeah. But I mean, if we at Connexus were asked to do this, what we would do, which granted is going to be on the high end of sophistication, we would run a leak rate model on the liquid leaking from something like, we would assume, like a pump seal failure. What is the rate the material is going to leak? That is going to determine the evolution of a pool. So how big of a pool are you going to get? Then we will run a vaporization model to figure out what vaporization rate we're going to get off that pool, and a dispersion model to figure out how big the gas cloud would be, and use scenario coverage to lay out our gas detectors based on that dispersion modeling. So that's that's the high end of what I would recommend. That's what we do, but I don't know exactly what your application is, because your application might be very compact and well confined to where you don't need to run dispersion models, because you know how big the gas cloud is and where it's going without running dispersion models. So it's really situationally dependent.
Yeah, and that's exactly the answer that I was looking for, because in my case, it's a pipe rack, is open, it's outdoor, and we need to run a dispersion model for sure, because there will be a dispersion cloud there for sure.
Okay. Well, also the thing to think about in a pipe rack is, what are your leak sources? So if you've got kind of seal welded flanges, a pipe rack is a very low probability leak source. So keep that in mind too. You're going to want to focus your detection on anywhere you have a lot of flanges or valving.
Yeah, that's exactly the point. And also there is a high probability of corrosion, and we are, and we're putting, corrosion monitoring as well, in order to prevent the whole thing. Yep. Thank you very much, Ed. Appreciate it.
My pleasure. Absolutely. My intention is to be done with these things in about an hour, but I just can't stop the sharing once the sharing begins. But thank you, everyone. I hope you were able to get an appreciation for where the 5-meter grid came from, what factors are baked into those assumptions, how that translates into a critical gas cloud size that you would use for geographic coverage. And thanks for your time. Thanks for your attention. And don't forget to, when you see that we've got this uploaded, share it with contacts that you think would benefit from this type of discussion.
Thanks again, everyone.